So I'm very pleased to be with you today for this fourth webinar about acoustic simulations. So my name is Diego Dudekem. As Christian said, I'm the head of the project and support team of FFT. FFT is an MSc company and is also the editor of the Actran software. So during the previous webinars, we have introduced the Actran software for acoustic radiation analysis, for strongly coupled vibro-acoustic analysis, and for aero-acoustic analysis. Today, we will focus on the Poro-elastic element library of Actran that is the key feature to model the damping of vibration or the attenuation of acoustic waves. The points we have on the agenda for today are the following. First, I will briefly introduce the poro-elastic formulation that is based on the theory developed by Mr. Biot. So this theory is based on the knowledge of several mechanical properties that are the so-called Biot properties. I will quickly review the major ones as well as the way these properties can be measured. I will then review the poro-elastic formulations that are available in Actran and compare them qualitatively with each other in terms of accuracy and performance. An important feature of Actran is the ability to compute energy balance statements in order to understand the physical phenomena occurring in the trim components. I will introduce this concept to you as well. We will then review some real-life application cases, and I will guide you through Actran VI, the graphical interface of Actran, during a live demo. And then finally, I will conclude this presentation in one slide, and then we will have our Q&A session. So, porous materials are used almost everywhere in the design process of finished goods, in particular for the design of all modern vehicles. They are the primary constituents of the trim components present in a car, such as the trim door panel, the headliner, the seats, or the floor panel. The main reason is that they are very effective to dissipate thermal or mechanical or acoustic energy. And in a vibro-acoustic context, the porous materials can be used either to absorb the acoustic energy or to damp the vibration of the structure, or a combination of both. Different formulations are available in Actran that are all based on the theory developed by Biot. So this theory involves the characterization of a vibrating skeleton that interacts with a surrounding fluid in the pores, and this fluid is usually the air. So the Biot theory is based on several assumptions. First, the heterogeneous medium is treated as an equivalent homogeneous medium with a solid phase and a fluid phase that are interacting with each other. The wavelength is assumed much greater than any feature of the porous material, such as the pore size or the fiber diameter. The displacements are assumed small so that the theory of linear elasticity can apply. The air phase is continuous and closed pores are considered as part of the skeleton. And as such, any effect related to the movement of air inside those closed pores is not taken into account. The model developed by Biot relies on the knowledge of several material properties. First, there are the mechanical properties, for instance, the Young modulus, or the solid density, or the Poisson ratio of the skeleton. Then there are the fluid properties, mainly these are the fluid density and the sound speed. And then finally, we have the properties of the foam, the so-called Biot properties, and those are the tortuosity, the flow resistivity, and the porosity. And the meaning of those properties will be explained in the next slides. So the porosity is the fraction of open area within the porous material, and as such, it is defined as the ratio of the fluid volume by the total volume of the foam. It can be accurately measured by placing a small material sample in a small cavity into a thick metal cylinder with a large thermal inertia. The porosity is deduced by monitoring the pressure in the cavity before and after the change of volume, assuming an isothermal compression process and neglecting the compression of the solid. We then have the static flow resistivity. So a fluid flow going through a porous material encounters a certain resistance related to the viscous interaction forces between the fluid and the solid skeleton. And the corresponding viscous force is proportional to the relative speed between the skeleton and the fluid. And so the flow resistivity is measured using a simple test equipment where a pressure difference is imposed between the two sides of the sample and the global air flux is measured. The resistivity coefficient measured by the device that is shown on the slide is a static flow resistivity because it is measured in steady flow conditions. We then have the tortuosity. So the tortuosity coefficient measures the complexity of the path of an air particle must follow to proceed from one point to another point. In a fluid, the particle follows a straight path, while in a porous medium, it needs to follow a tortuous path around a solid frame. And so as such, the tortuosity is always greater than 1. So the tortuosity creates a mass coupling between the skeleton and the fluid, and an ultrasonic technique can be used to measure the tortuosity. And in this technique, a thin sample is placed between an ultrasound source and the receiver, and the propagation speed with and without the sample will characterize the tortuosity. Let's now consider the different porous models that are available in Actran. The first one is the so-called porous UP model. This model is the most complete one and without any assumption that is made to the equation of Biot. Each node of a porous UP finite element carries 4 degrees of freedom, meaning that there are 4 unknowns that are solved by the algebraic solver implemented in Actran. These 4 unknowns are the solid displacement in the 3 directions, and by solid displacement one means the skeleton displacement, and then the fluid pressure within the pores. The material properties required are the elastic properties for the skeleton, the acoustic properties for the fluid, and the Biot properties for the interactions between the solid and the fluid phases. The complexity of the model can be further extended using the Johnson-Hallard micromodel when the thermal and viscous lengths are available. And this can be done to take into account the non-uniform dimensions of the pores compared to the fluid channels. The full UP model is usually required when there are important elastic deformations, typically when the porous medium is placed inside a multi-layer sandwich panel between a primary thin structure and a septum. We then have the lumped and rigid porous models. Those two models are simplified versions of the porous UP model. In both of those models, the behavior of the skeleton is eliminated from the system of equations thanks to a simplified assumption. On the one hand, the porous rigid model assumes that the skeleton is perfectly rigid and has 0 mass, so that the solid displacements are equal to 0. On the other hand, the lumped porous model assumes that the skeleton is a perfectly soft lumped mass, so that the solid displacements equal the fluid displacements. And for both models, there is one single degree of freedom, that is the fluid pressure. There are less material properties required than for the porous UP model, only the fluid properties and the Biot properties, plus eventually the solid density in the case of the lumped porous model. Those simplified models are usually sufficient when the porous medium works in pure acoustic absorption. And in many cases, the lumped porous model is more accurate than the rigid porous model, mainly because the inertia effect of the solid is accounted for. The price to pay is the knowledge of the foam density that is required, but this is usually not a very complicated quantity to obtain for measurement. 2 other models are available in Actran, and those models are the semi-empirical models of Delany-Bazley and Miki. Those models are fluid equivalent ones, in the sense that they are based on an equivalent complex sound speed and equivalent complex density that are frequency dependent. For those models, the unknown per node is also the fluid pressure. These two models are popular because they only need a very limited number of material properties to be known. Typically, only the fluid parameters plus the porosity and the flow resistivity are required. To compare those different formulations with each other, two test cases have been set up. The first case reproduces a standard cone tube test where the sample is fixed to a rigid support and one looks at the absorption coefficient of an incident plane wave. And for all cases, the reference is the Porous UP formulation. Three different samples of porous medium are considered. First, we look at a low density foam. Then we look at a high density foam. And then third, we look at a rigid plastic foam. And for the high density foam, all the formulations match pretty well with the reference Porous UP model. For the low density foam, the lumped model fits much better than the other models. And for the plastic foam, none of the equivalent fluid model is able to capture the skeletal resonance occurring around 1 kHz. The second test case considers the transmission of an acoustic wave through a porous medium fixed to a vibrating plate. In that case, the indicator of interest is the radiation efficiency of the plate, and again, the reference is the Porous UP formulation. For the low density foam, the lumped model again outperforms all the other formulations. For the high density foam, the rigid porous and the lumped porous models are good approximations, except around 200 and 300 Hz, where they are not able to capture some phenomenon occurring in the skeleton. And for the plastic foam, none of the simplified models is able to correctly represent the behavior in transmission of the system. So the Porous UP formulation is really required. Many industrial applications where the reduction of acoustic transmission is required involve what we call sandwich structures. In those applications, one typically tries to reduce the noise transmitted from one side of a metal structure to the other side. And this is done by adding a layer of porous medium with on top of it a layer of septum. Such septum has typically a high mass and a low stiffness. And thanks to this, the vibration patterns in terms of wavelength and amplitude of the metal sheet and of the heavy layer are completely decoupled from each other. And because of that, a strong dissipation can occur in between, that is, in the porous layer. Actran automatically computes the amount of power dissipated by the different phases of the system, such as the structural deformation of the skeleton, or the thermal effect in the fluid phase, or the interaction between the fluid and the skeleton through friction, for example. And using those quantities, one can plot energy balance statements such as the one presented on the bottom right of the slide. So in the next slide, we will review some examples of application. The first example concerns the reproduction of a test setup involving a frame connected to a simplified trim component that is a sandwich panel. The frame is excited by the mean of a shaker, and the upper side of the trim is placed in an anechoic room. Two samples of porous materials are compared, a foam material and a fibrous porous medium. The numerical model is made of structural and poro-elastic finite elements to represent the frame and the different layers of the trim component. But it also includes acoustic finite and acoustic infinite elements to represent the free field acoustic conditions. On the top left of the slide, one looks at the acceleration at one point of the steel plate for the fibrous trim case. On the top right, the mean velocity level of the carpet is plotted for the same trim. On the bottom, one shows the pressure, the sound pressure level at 1 meter of the trim for the foam case on the left and for the fibrous case on the right. And in all figures, the dashed blue curve is the simulation, and the solid red curve corresponds to the experiments. And we can see that in all cases, the agreements between the numerical results and the experimental results are fairly good. Another trim application case is presented in this slide. So in that case, one compares Actran with experiments for assessing the effect of a floor trim panel that is mounted on a car body excited at the engine mounts. On the left-hand side are presented examples of experimental structure transfer function at the bottom and acoustic transfer function at the top. On the right-hand side, the equivalent numerical results are provided. The behavior of the system, and in particular the attenuation brought by the trims, are correctly reproduced by the numerical models. The next example concerns the transmission through a dashboard and the evaluation of the efficiency of sandwich patches. The key ingredients for such model are the shell elements for the dashboard, the porous and visco-elastic elements for the sandwich, and the acoustic elements for the car cavity. Because of the complex damping mechanism occurring in the sandwich, typically one will use a direct frequency response to compute the analysis. The output of interest of such analysis are the vibration levels of the dashboard and the sound pressure levels inside the cavity. And the influence of the car body on the response of the dashboard can be accounted thanks to the import of a super element for NASA. So the purpose of this last model is to compute the transmission loss of an automotive air filter. So the structure of the filter is made of plastic and the interior is filled with air and porous layer. To model the inlet and the outlet ducts, a specific boundary condition of duct modes is used. The transmission loss is computed with and without the porous layer in order to assess the effect of this porous layer. The energy balance is also plotted to understand the physical behavior of the system. And one can also look at structure deformation or sound pressure level maps. Okay, now I will guide you through the graphical interface of Actran during a live demo. So in this demo, we will assess the efficiency of a trimmed dashboard in acoustic insulation. So in this example, a layer of foam and a layer of septum are added to the steel dash panel, and this sandwich panel is connected to the car compartment. So three configurations will be compared. A first model only involves the bar dashboard made of steel. Then we will consider a second model that is the dashboard plus a layer of foam. And then a third and complete configuration will also be computed, that is the sandwich structure with heavy layer. So the demo will involve the construction of this complete model, and the other two more simple models will be created starting from this complete model. So the prerequisites to build this model are two finite element meshes. A first mesh representing the trim dashboard with a set of 2D elements for the steel, a set of 2D elements for the carpet, and then a set of 3D elements for the porous elements in between. The second prerequisite is another mesh that should include 3D elements for the acoustic fluid and a set of 2D elements for the coupling with the dashboard. And so the fluid structure coupling will be done through an incompatible interface so that the two meshes can be created completely independently. They can have different mesh refinements, and they can include even some small geometrical differences. And so the desired output of the analysis will be the sound pressure level at the driver's ear for the three different cases. So let's now leave this presentation and move to Actran. So here is Actran VI, the graphical pre- and post-processor of Actran. So on the right-hand side, we have the render window where the model will be displayed, and on the left-hand side, there is the analysis tree. So the first step is to import the mesh that has been created earlier. So we support various formats like the NAS and BDF, but here we will import the mesh in the Actran format. Here we go. So the first thing I'm going to do is to change the colors of all that and try to identify what are the different parts of this mesh. So first of all, I have the dashboard here that is made of 2D elements. Then connected to this dashboard, I have the 3D elements for the porous material. And then connected on the other side of the porous elements, I have a domain made of 2D elements again, that is the septum, the heavy layer. So that's for the structure. Then for the acoustic part, I have the acoustic cavity made of 3D elements, and at some of the three faces of these 3D elements, I also have 2D elements that will be used to make the coupling between the structural part and the acoustic part. And I also have something important to mention is that I have also 1D elements that are around the dashboard. And on these 1D elements, that's where I will apply the support condition for my dashboard. So the first step in the creation of the analysis is to create the required material properties. So first, I need to have a fluid material properties for the cavity. So I will create a material which is a fluid material with standard properties. So if I want to display the default value, I can simply click here. Then I will create other materials for the steel, for the foam, and for the septum. But instead of creating those materials from scratch, I will import those materials from the database. So I will import the foam material. I will also import the heavy layer material, and I will import the steel material. Let's double click here on the foam to have access to see all the properties required for a porous material. So you can see that part of the fields here are blank, meaning that default values will be used. And so this field can be left blank, or to access the default values, I can click here, as I mentioned earlier. So now I have my materials. So next step is to create the analysis. So for that, I go here in the left-hand side, the analysis node. I right-click, add Actran analysis, and I will select the direct frequency response. And you see now on the left-hand side, I have here an analysis tree with all the different parts that I need to create for my model. And the first thing I will do is to create the different components needed for my model. The first component that I will create is a thin shell component for the steel plate, for the steel shell. First I rename it, then I will assign the proper material, and then I need to define a mandatory parameter, which is the thickness, and my steel shell makes 2.5 millimeters, so that's what I enter here. And then I will apply these properties to the related material, which is here my dashboard steel domain. So you see here now on the left-hand side, I have the component that I have just created that has appeared in the tree. So the next component I will create is the Porous UP component. Again, I need to point with the valid material, and I will select my foam domain. Then third one will be my septum. Here I will rename it for the process, and here again I need to enter the thickness, and the thickness of my septum is decided to be 3 millimeters. And again I need to select the right domain, which is here the septum. Okay, and last but not least, as a physical component, I need to create the acoustic fluid for the cavity, to refer it to the valid fluid material and assign it to the cavity element set. So now on the left-hand side, I have my acoustic cavity, I have my septum, I have the steel, I have the porous material. So I have all the physical materials needed. but I still need to couple the structure and the cavity. And that's done through first a definition of coupling surface. So first an acoustic coupling surface that will be applied here to the 2D elements. And then I also need to create a structure coupling surface and the structure coupling surface will be the septum, because I want the cavity to be connected to the septum layer. And then to actually make the connections, I need to couple these two coupling surfaces with each other, and that's done through an interface where I will select the two coupling surfaces. Here we go. And I'm going to change here localization parameters because I have a small geometrical mismatch between the structure and the cavity. So I will say that I have a 10 centimeters allowance between the two. Okay, so when this is done, I have all the components needed for the analysis. But besides the components, I also need to create the boundary conditions. So there are two boundary conditions I need to create. First, the support conditions that will be a zero displacement in all directions for all the nodes of the edges of the dashboard. So here I say that I want zero displacement, and I will apply that to the edges of my dashboard. And then as an excitation, I will apply a constant and uniform pressure field on the dashboard. And so for that, I will create a distributed pressure that will be 1 Pascal uniform pressure, and I will apply that on the dashboard. Okay, so now that this is done, I need to specify the frequency range for the computation. So I want in this analysis to go from 70 Hertz. I want to go make the computation every 1 Hertz, and I want to go up to 330 Hertz. Then I need to define an algebraic solver. I will take the fast FRF Krylov solver, and I will ask as a subsolver the Muntz solver. And then when this is done, I'm almost finished. The only thing I need to do is to define the post-processing quantities. So in my case, what I want is to have the sound pressure level at the driver here. So I need to create a microphone for that, what we call a field point in Actran. And so I go here. I know the coordinates of my field points. So my field point should be located at 2.19 in X, in 0.47 in Y, and in 1.11 in Z. And I will here create a field point out of that. And so if I try to visualize these field points, okay, I will put it in red. Here we go, and I can see here, you see it's not completely clear, but here where my mouse is, I have indeed the field points that has been correctly created. Okay, very good. So then I need to specify also the name of the output files where the frequency response results will be stored, and it's called a PLT file in Actran, and so this name that will be named sand.plt, sand for sandwich. Then I may want also to create to have maps of the analysis. So for that I need to create an output map component. I will take the format as the NFF format, which is the Actran format. The result file will be called sum.nff, and I want that to be output every 10 frequency of computation. And I want the results to be stored on the cavity, sorry, and to be stored on the dashboard for having the deformation. Then when this is done, I think I'm okay. So I can output the analysis to run it. And so for that, I will here, create an input file. Yes, I want to replace the existing file. Yes, I want to. Yes, here we go. So now I have created the first input file corresponding to my complete configuration. But now, starting from that, I want to create the two other more simple cases, meaning first I will create the case with steel plus foam. So for that, I need to remove the septum from the analysis. So it's down here. I simply press delete, and then the component is removed. And then I will simply need to change the output file names so I don't override them. Here we go. And then make the export analysis, foam input, yes, yes, I want to erase it, yes. And here we go. And so last but not least, to create the steel case, then I don't need to remove the porous UP component, but I need to transform the porous UP component into an acoustic component. So I will shift my elements, my finite elements from porous finite elements to acoustic finite elements. So I go here and I select finite fit. I apply the right material to them, and then that's it. And then again, I export the analysis. Oh no, one thing I need to do is to change again the name of the file. Steel.plt, and here steel.nff, and then I can make the export. Shoot. Here we go. Okay, so then the next operation is to run the analysis. So I can do that directly from Actran VI, or I can launch it in a prompt. To gain some time, I've already done that. So we will directly look at the results. So here are the three results files: the steel PLT, the foam PLT, and the sandwich PLT. So I will look and plot the sound pressure level at the drivers here. So I go here, and under field pressure, I right-click, plot dB pressure. And then I do the same for the foam. First change here. Steel. And then I do that for the foam. Oops. This is steel plus foam. And then finally for the sandwich. Oops, I'm going to change the color. So this is my sandwich. So analyzing those results, I can see that first of all, those three curves are different, and so indeed the addition of the septum strongly changes the performance of the system. We can see that at low frequencies, at some low frequencies, I have an amplification of the noise, and that is expected. But at higher frequencies, let's say starting from 270 Hertz, I clearly have a strong decrease of noise, a strong attenuation, thanks to this to the addition of the septum. So it's really the addition of the septum that makes the dissipation occurring much more in the porous layer. So obviously, I could also look at maps of the system. Here, for instance, I'm comparing on the left-hand side the case with the septum, and on the right-hand side the case only with steel. And so I can look at the pressure field inside the cavity for the different frequencies. So obviously, this is also something that is perfectly feasible, but we are a bit running late. So that, I think, will close the demo, and I will go back to the presentations to make the conclusion. So during this webinar, The poro-elastic features of Actran have been introduced, and the major material properties, so the so-called Biot properties, have been reviewed. So as you have seen, different formulations are available in Actran. First of all, we have the Porous UP formulation, that is the most complete formulation and the most accurate one, but that is also the most costly in terms of computational requirements and also required mechanical properties. On the other hand, we also have the lumped Porous formulation that offers a good compromise between accuracy and performance, and that is very suitable for a vast majority of applications. The other formulations are often less accurate, but have the advantage of requiring the knowledge of a smaller number of parameters. So we have reviewed different application cases, including some validations with experiments. And it is important for you to remember that the poro-elastic material library is really a key ingredient to handle more complex problems that are trim body simulations. And those trim body simulations will be the topic of one of our next webinars in the coming months. So I thank you very much for your attention.